And hello, Dr. Tofu. Thank you so much for joining us for our Women in STEM month. Guys, a streamer that I look up to immensely. She is a real-life physicist, doctor, PhD in physics, partnered Twitch streamer. Welcome onto the show, Dr. TinyToxicTofu.
Thank you so much for having me. I'm really, really happy to be here. I am from Ireland. I have a bachelor's in physics and chemistry education. Went into a bit of teaching, decided I didn't really like kids. So I quickly switched route. I did an applied physics master's degree, went on to do a PhD in batteries and the Irish electric grid. And now I am a full-time lecturer here in Ireland, which is incredible to be able to become a lecturer immediately after graduation. I got very, very lucky. But I'm also an avid science communicator via Instagram and Twitch. So I teach physics mostly to people who are just getting curious about physics. So do you know the way there's amazing YouTube channels like Veritasium and Kurzgesagt, and they teach like very fluffy physics, if that makes sense?
Yeah.
You know, like with all the wonderful space launches that are happening, everyone's getting really excited. And basically, I'm your introduction of, if you actually want to start learning basic physics, then I start doing that kind of stuff. That's my shtick, if that makes sense.
So just a generic question for you. Why do you think it's important for many people to learn about physics? Like, what does the everyday person, why is it beneficial and enriching to the everyday person's life to learn some physics?
That's a really good question. I would say that, generally speaking, that y'all are doing physics without realizing it. I think that is something that kind of has to be accepted. Physics is in every bit and ounce of your life, no matter what field of science you do. So yes, biologists are physicists at heart somewhere deep inside, but also like just living your life and everything that you do, whether it be repairing anything at home or building things, working at your PC, in some shape, way, or form, everything can be led back down to the creation of a physicist, number one, and number two, your leading of the understanding of that realm also leads back to physics.
Bart Hackey suggests the possibility of sports as well involved.
Yeah, absolutely. So, I love teaching rugby. Rugby is a huge sport here in Ireland. We're one of the greatest rugby nations in the world, which is a rare thing to say for such a small island. But I love teaching the physics of rugby, whether it be the momentum of the players. Some of the collisions are insane, and the way they pass the rugby ball, which is very similar to American football. So the physics would apply very much similarly.
So one really cool thing that I love about your channel is how you teach the physics, right? So like you said, that teaching in the context of rugby is a way to make it accessible. What are some other ways that you also teach physics on stream and maybe even in the classroom that make it easier to connect with?
So the thing that I do on Twitch is that usually the physics that I teach is inspired by the game I'm playing. So I'll actually be on the front page next weekend, just after International Women's Day, and I'll be teaching Marie Sklodowska-Curie's work on radiation, but it will be leading into Half-Life. So if anyone knows Steam's and Valve's famous game series, so hopefully we'll know everything about the physics of Half-Life before actually playing Half-Life. And that's the way I tend to do it. I try and find interesting and fun topics in video games to teach people. And as Zir has pointed out in the chat, I upload videos of me doing weird mathematics and weird physics moments in games where it was an accident. I killed a character. It wasn't on purpose, but we calculated a centripetal force in rotation, and we measured his launch velocity. You know, you do all these like little fun physics stuff in the games.
And are you going to be looking at I think the crowbar, right, is one of the main weapons in Half-Life? Are you going to be looking at any of the physics of how to like get into some of those doors?
No, I didn't even think about that. The crowbar was very significant in Half-Life. I didn't even think about that. No, I was mostly looking at the fact that, you know, Half-Life have the lambda in their user in the title, but that lambda isn't Half-Life. Half-Life is t to the minus half, so it's...
See, y'all, we're going to find out some physics in Half-Life. The other one I really enjoy you playing is God of War.
Yeah, that was fun. I don't do much physics there.
There was still some. You were yeeting some enemies, right? And you were calculating like the velocity of where they were going and how it was trying to be connected. So it's a really clever way of making physics accessible. And before we get into how you personally got into physics, What got you into science communication? What got you into the idea that, you know what, this is important for people to know of and make accessible to? What was it?
Yeah, that is very interesting, because I was a Twitch streamer for a very long time. I used to play, I want to say semi-professionally. It's not really semi-professional, but a different game called Heroes of the Storm. It's a MOBA. If there's any Blizzard fans in the chat, they know what I'm talking about. I used to be a Diablo OTP, played him as a tank, and I used to stream for years that game competitively. And then I abandoned the game. There was bad blood, not with anyone, just like the game itself. It's very toxic, and you can imagine a negative community can build up if you play any MOBA. And I started streaming variety games, but in the process, I realized that everyone has to have a shtick, if that makes sense, a selling point when you're a Twitch streamer. I didn't know what I could provide. I didn't know what I was unique at. And it just happened to be that we were discussing Alan Turing. I pulled out Alan Turing's paper. We sat down as a stream, read it together, and yeah, that's how that little ball started rolling. That so many people were chatting and communicating about Alan Turing's paper, and after that, it twisted into physics.
What is the paper about?
Oh, it's the imitation game. So it's the infamous paper that he wrote, absolutely ahead of his time, where he talks about how a computer could pass a test where it could falsify itself as a person, as in could pass itself as a human being.
That is really cool. And so how long ago was it that you started changing the stream into one of these much more like educational based, like looking into those papers and like making everything a slant that maybe not necessarily even about physics at first? Like, how did it become what it is today?
I suppose started it almost 2 years ago. It was towards the end of my PhD, and it's actually how the Instagram thing happened. I never posted an educational thing on Instagram about my physics. I published my thesis. I finished writing my PhD thesis. I had a few weeks break. I went to watch Oppenheimer in the cinema, and there was just a really cool moment that happened. No spoilers, but there was an atomic bomb test, okay? FYI, in case anyone doesn't know about this. And there's a wonderful scene where just before the test happens, Feynman is sitting behind the screen of his Jeep, and people are saying, oh, you should put on your glasses. And he says, oh, don't worry, I don't need to. The windshield will protect me. And the idea behind it is that UV doesn't penetrate glass. That whole principle is the basis of why, if you do any spectroscopy analysis, to get into the UV spectrum, you can't use glass. You actually need to use quartz. There's other little materials that you can use. Anyways, I did a whole little spiel on Instagram. It kind of blew up, and that's how I was like, oh wow, people are actually interested to learn about science, about physics in everyday life. So that's how that rolled as well.
So, Dr. Tofu, take us back. What got you originally interested in science, and was it physics to start with?
Actually, unfortunately, don't have an inspirational story. I was just good at maths in school. In Ireland, we have this system kind of similar to the US, where you have middle school and high school, where we transition from junior cert to leaving cert, and we have to pick a few subjects to specialize in. And I selected 4 subjects, actually, which was really rare. You were only supposed to do 3, but I chose biology, chemistry, physics. I did all 3.
Nice. And
then I took an extra 4th one, applied mathematics, which was really, really helpful. Very good subject for later in life. So I did all 3 subjects. I got a taste of all 3 sciences. And when it came to going to college, I still didn't know what to do. I was good at maths. I liked physics. It was grand. I kind of mostly applied for the secondary school teaching course because, just to kind of give a bit more background and information, that even though I'm from Ireland, my parents actually immigrated in the 90s, and we weren't very well off. And so when I was looking at university degrees, the education is not technically free, but it is free in Ireland, as in it is affordable. But I knew that I needed to be employed. So I was looking for a job with employability, and there was a shortage of physics teachers in Ireland at the time. Honestly, that's the reason why I picked it. I thought about getting employed as quickly as possible and having a stable income so that, I wasn't a burden on my family.
And so in that line of education, what parlayed you into getting a physics PhD?
So the master's was the first turn. I had to do the master's first, but it was actually my thermodynamics lecturer. Absolutely amazing lecturer. He was so passionate about physics. And if you speak to physicists or scientists, it's not thermodynamics that makes you a physicist. Usually it's particle physics, quantum, those kind of things. Thermodynamics is the thing that everyone survives. But he was so enthusiastic and so passionate about his subject. He made me fall in love with thermodynamics as well, which led me on to apply for a master's degree. I got a scholarship that was incredible. I couldn't believe that I applied for it and got it, which then, because of my good grades, I was able to get really ease in comfortably into a PhD program. And that's how it happened here. It was almost accidental. I like to describe that my whole course of getting my PhD and being a physics lecturer to this day is a series of unfortunate events, if anyone knows the books. Yeah. It just happened in a way that none of this was planned. Life was hard at the time. There we go.
So being in physics and going into the program, what does a master's program look like? Is that something where you're also working in a lab? What is a physics lab? Yeah. Like, what does that even look like? Because we talk here about the biological lab and a wet lab or even a computer lab. As a physicist, I feel like there's two possibilities that people might think of. One is that you're dropping an apple, right? And thinking about what that means. And the other is you're working with like nuclear bombs.
Yeah, unfortunately, I do neither. Yes, yes. So my master's and my PhD were both in a lab. A lot of it was laboratory based. Specifically, my degree was in applied physics. If you've watched Big Bang Theory, there's basically two sides of the coin. There's the theoretical physicist, which is Sheldon, and there's the experimental physicist, which is Leonard. I would be the Leonard if you want to kind of have something in your mind. And so, honestly, a physics laboratory is basically a chemistry lab, but with no rules. And I know that sounds almost bad, but imagine that you have loads of experience in this, and you know that in biology there's a huge safety procedure in anything. Like you said, wet lab, dry lab. There's different rules and certain legal procedures. In chemistry, there's all the chemicals. In physics, like you said, unless you're working in nuclear, nothing is usually dangerous. So there's no lab coats usually. There's no scary like supervision processes involved. There's obviously the general health and safety, of course. But yeah, I always kind of describe that physicists are chemists on the loose. That no one is looking over your shoulder to make sure you're not going to do something silly or dangerous. But yeah, I would describe it very similar to a chemistry lab, but also a bit more what's the word? Hands-buildy. Like most of the things that we build in the lab is very crudely done. I had a very simple experiment where I needed to keep vanadium, it's an element I worked with, at a certain temperature, and I needed to keep it floating or whatever. Literally, we bought a plastic box. Massive plastic box. We rigged a kettle to work with an American transformer at a lower voltage so that it would slowly boil kettles. We bought this little Tiki Max thing pump that would pump water from the kettle back into the bucket. And what else did we do? Oh yeah, we had thermocouples to equilibrate the temperature. It was so crudely done, but it was so ingenious as well. Do you know what I mean? It was so simple that you're the
modern day MacGyver, right? So like,
but you know what? That's not far from the truth,
right? You're coming up with innovative ways to get to the answer, right? By building custom things. So did the lab just look like someone's cool garage with just like a better quality toys?
Well, I wouldn't say it's better quality. Still, yeah, it was. Physics department is not very well funded on a budget in weird ways. Yeah, but it was a mess, as in it's absolutely cluttered, and we had access to some of the really cool old equipment, really old classical potentiostats, little things like that nobody would really use nowadays, especially in any advanced lab. But if your experiment is very, I don't mean this in an insulting way when I say primitive, but if your experiment is very, very basic, number one, it's simple and easy to fund and all of that. But number two, your results cannot be argued. If you're an experimental physicist, you do not want to publish results that are arguable, that someone can deny or falsify in any way. So if your experiment is as basic as it gets, down to the basic principles, you have a very good experiment and very good publications.
When you started your master's, how did you choose your research question? Because you can tell me if I'm like mistaken here, but in biology, it's like, oh, I'm just looking at something that's it's like, well, how does that work? And it's like I see an animal moving and I'm wondering like how it does its wiggling. In physics, right? Like, how did you pick your question? Like, how did you think of this is interesting and this is what I want to spend the next couple of years asking questions about?
Yeah, if we see something wiggling, we slap it. It's like, no, stop wiggling. You're not meant to wiggle. No, don't do this to me. Don't do this to me. So in physics, no, we were very, very peculiar. Like, it's definitely a thing where you have a research group. They have an idea for an experiment. They ask you to do the experiment, and then they'll see stuff happen. And they're like, interesting. What if we, like, what's the consequences of that? And you just branch off. It's basically like a Twitch streamer that goes on a tangent. I'm totally not speaking from experience, but do you know the way a streamer's topic can derail over time?
You mean the rabbit holes like we have here, where it's like you're like, we're going to talk about octopi today. Oh God, we ended up in microRNAs in a frog, like totally unrelated.
Absolutely. So that is basically how research is done in my group. Well, it was done in my group anyway, and I don't know if it's physics as a whole, but that is definitely something that happens. A PhD is usually a tangent, and I don't know if anyone else writes their PhD thesis that way, but I ended up writing my PhD thesis that way, where you have to craft a story afterwards, and you do need to link your tangents together. So the old school classical way of the way a PhD is done is that you have a thesis with something like 3 original chapters. Most people do by publication now. I did it the very old school way here. And you have to craft a story as to where chapter 1, chapter 2, and chapter 3 link up. And then there is this big kind of conclusion or aha, look what I've done moment. There's always that one chapter that is a disaster, I think is a fair thing to say to many people. There's one chapter there like, that we just put that in because of the story. We needed to put it in there just to make sense.
So what was the story of your master's and your PhD work?
Yeah, so we could talk for a while here if that's okay.
Please.
I've prepared for this. So my master's was actually in something a bit very minute. It was in a field of nanotechnology where we were actually looking at the electrodeposition of copper, depositing copper on thin films using electricity, electrodeposition. And why this is important is basically if you look at your PCs, everyone turn right, turn left, wherever your beautiful PC is, and you see your motherboard, if you have a glass, a glass overview, don't touch your PC if it's running now. It's hot. Don't touch it. But in the motherboard, you have all these integrated lines, all these deposited metallic lines. And I was basically studying that as you deposit copper over and over again on top of each other, grains form, literally like circles begin to form. And not only that, depending on the rate that you deposit, depending on temperature, depending on all of these things, they would cause stress or strain. Now, why this is really important to study is because over time, your integrated circuits will fall apart. They will cripple. And basically, I was studying and observing this under a scanning electron microscope. And yeah, it's really important not only in integrated circuits and nanotechnology and semiconductors, it's also important in battery technology and any, you can imagine the application of this is very, very universal.
So you're looking at a scanning electron microscope is what you're taking these images under, that's kind of cool. So we've talked about in the context of biology, it's really neat to then see it in a totally different field, still being utilized to be able to see the details. Like when you're looking at that image, what are you looking for to be able to tell you when something's happening, or it's not the case?
No, it's not even that we were looking for something. We were just looking at what it was.
Cool.
It wasn't that we were looking for a needle in a haystack or anything. We don't know what it was, and so we were just observing that.
So it was the question was framed in a way where, regardless of what you found, it was going to be cool.
Exactly. Like we don't know what it is, right?
Nice.
That's exactly what we're exploring. So that was kind of my master's research. My PhD kind of led off in a different way, and overall, the picture of what I did is called, well, no, I don't know if it's called, but the overall picture of my PhD is that I studied the synchronous Irish electric grid. Most electric grids in the world are synchronous. And I was studying its stability and about the possibility of introducing a stable energy storage source, such as vanadium flow batteries. So that's a beautiful one sentence to describe my PhD research, which, it really isn't just one sentence when you go down to
So So dissect that for us, Dr. Tofu. Like, in the most rudimentary way, like, what is the problem that you're facing? What was the need for it? And then how did you go about answering this kind of question?
Yeah. Do we have time? I don't know how long. Like, everyone need to go to bed, or what's the story with everyone? Do we have time for this? Because I have a plot. I have a plan of how to explain this, hopefully in a nice way to most people. And the reason is that most grids are synchronous grids, and I'll explain that in a second. But the reason that I want to highlight this is you'll hear in the news all the time that, we can't introduce renewable energy because, what will they usually say? They'll say, because it's too expensive, or it's unstable, or it's not the right area to build things. They'll say all these kind of things. And in reality, that's not true. Well, maybe there is a certain truth, but that's not the major problem. There's a bigger hill that we need to get over first. So to quickly explain, classical way the electric grid operates is that you have these large generators that are operating connected synchronously to the grid. This means that a generator is spinning around in circles really, really fast. Steam heats up, it moves the generator moving really, really, really quickly. And in Ireland, we happen to operate at 50 hertz. To everyone in the United States, you guys are operating at 60 hertz. Doesn't matter, it's just a number. And these guys are all spinning. So let's say, I always like to take the example of Ireland. It's an island. And let's say that we often need about 3,000 megawatts of power at any given moment. And we have 10 generators all producing 300 megawatts around Ireland. And they're all synced up to the grid. This means that, let's say a disaster happens and one of the generators collapse. This means that your frequency is now for operating at 50 hertz, and it's about to drop. It's about to drop to 45. We're about to panic because this is where blackouts happen. And before this happens, there's a couple of things that are in place to protect it, because we are a synchronous grid. Number one, the generator that has shut down has inertia, right? It's spinning, obviously, because of the steam, and suddenly the steam isn't there. It can't move anymore. It's not synced up, but it still has momentum. The big wheels are still spinning. That buys you a couple of really important seconds. The other important thing is the other 9 generators that are all over Ireland are now operating at 100%. Before, they were only operating at 95%, but they registered that one of the generators is down, so they up their game. They start operating at 100.
So you intentionally lower the percentage operating threshold to account for if there's a loss.
Exactly. Okay. So they respond with that. There's also other stuff like open cycle gas generators that are specifically mini gas generators that are operating at 10% that will sync up immediately to respond and rev up to 100% to respond to this. But basically, this is the power of a synchronous grid. It means that if there's any fluctuations, if there's any losses, with the inertia and all the other electric grids, electric generators that are connected, there is a way to respond very quickly to this situation.
You said that when that first one shuts down, you have a couple of seconds, and those seconds are important. So I found that little statement to be really cool. Like, what makes those couple of seconds really important? Like, why is that buying you time? Is it just for the other generators to kick in?
And not even to kick in, to get the next generator up and running. Gotcha. So ideally, what you would do is your 11th generator is coming in, right? Okay. The spare generator.
And the spare generator,
but that all takes time.
Until now, is not even on.
Yeah, exactly. Like, you really do need to boost it. It takes so much time, and all of these. When we're talking about response time, this is something that I'll say. Sometimes it's less than a second. Like, that is how fast response times need to be.
Wow.
Very, very difficult. Now, here's the problem. We're introducing renewable energy to the grid, which is great. I'm not an anti-renewable before anyone comes at me, I'm very, very pro-renewable. I'm just explaining the problem to anyone to make them understand. So now, let's say we have 6 generators on the grid, and we replace 4 of those generators with solar and wind. Great, awesome. But those are not synchronous forms of energy. They're not generators. They're not heating up water to make steam to make a generator go. They're directly connected to the grid. If you want to kind of have a DC AC mind about it, that's kind of how it works. So now we're going to another story. Now one of the generators collapse. You now have only 5 generators that are integrated to the grid who are operating at 95%. Now it cannot respond quick enough with the power output that you need. This is a huge issue with the more that we integrate renewable energy with the grid, because if there is any huge downfall, any generator collapse, anything, we don't actually have that ability to respond very, very quickly. And this is a whole field of physics and science to do it. There are little things that are in place. Oh, sorry.
No, so why is that inherent to renewable energy? Like what is it about the renewable energy sources that makes it in a way that it's hard, or is it just like how it's integrated into the system?
So it's not a generator that's moving. So you might think wind turbines might be, but they're not synchronous. You can't force a wind turbine to operate at 50 hertz, for example. You
Gotcha.
know, you get whatever wind you get is what you get. It's actually interesting. If I'm not mistaken, I could be wrong. Don't quote me on this. But the generation of the wind turbines is AC initially, converted to DC, which is then again converted to AC. Wholly inefficient process to actually do it.
Gotcha.
And then solar panels are directly constructed with DC in mind as well. And yeah, wind turbines can kind of not meet the requirement, but try and buy you time to offset this by sometimes. There are wind farms that will actually move the pitch of the blade so that they're not maximizing the power output. That means they're operating, let's say, at 80% efficiency. And so when there's a power outage or a power plant that collapses, they change the angle so that they are suddenly, boosting up the power, which is a great idea. But again, it takes time. I'm talking about several seconds here at least. And that is already very, very, very costly.
It's cool. It's really cool. The time factor that you're highlighting here is that, one might naively think that a few seconds is fine, but it seems like that is a big limiting factor in making this work successfully. That's a really, I love the details, Tofu.
There are solutions in place that we have things called like synchronous condensers on the grid. I know that Ireland did get them in at one point, but they're weird. It's basically a thing that spins that you integrate with your grid, but you're feeding it power to spin so that if there is a power outage, like a generator collapses, the inertia of that spinning thing is then used to buy you a couple of seconds. But hopefully it's clicking in. This is completely wasteful. We are quite literally putting energy in things just for what ifs. Does that make sense? We're the blade of the wind turbine, for example, we could be harnessing 100% of the wind, but we're not because we're worried about the what if. We have these spinning condensers that we're literally putting power into to make them spin on the electric grid, just so that it has inertia for the what if.
That was actually a what if question in chat too. What if a second one goes down, like a second one of these power supplies, right? And how does that end up happening into it? So what's the solution then? How do we get rid of the what ifs?
If you have a second generator that's collapsed, ladies and gentlemen, that is what classically is called a blackout. So if you are in a city or an area that experiences this is a problem. That is the ultimate consequence. That does happen, or if you don't respond correctly.
There we go.
If we can't respond. So yeah, maybe some people experience blackouts. I live in an area where I don't. Very, very lucky. But generally, Ireland is pretty good. So all of these problems with the electric grid that I've described is universal across the world. This is a thing. And it doesn't even matter if it's renewable. It's just introducing any other form of energy that isn't a generator that is synchronous to the grid. Anything that is not a generator, usually powered by steam, anything that doesn't spin is going to be a problem. And what we need to do is find ways to respond to the grid very, very quickly. And that's where my research went into vanadium flow batteries. Vanadium flow batteries, one of its selling points is that it can respond to the electric grid very, very quickly. So that's part one of my PhD. Explained a little bit.
So how does this happen? How does the electric grid, how does it respond quickly? Where is it built in? What is unique about this battery? Can I use it to charge my phone? What else can I do to make something like this work?
Okay, so I guess I'll explain very quickly. No, you can't use the vanadium flow battery to charge your phone. A vanadium flow battery is not a lithium ion battery. It is not a super energy condensed battery, which means that it's not small. It's very, very, very large, very, very, very big. big. And because it's very, very big, we can't drive around it, or we can't move it around or anything like that. But what's really useful about it is that you can scale it up to whatever size you want, which makes it perfect for electric grid integration. So if it's okay to explain what vanadium flow battery is.
Please.
So a vanadium is an element. It comes in a crystal blue powder form. Let me check. 2 seconds. Aha! And we dilute it into electrolyte using H2SO4 and water. It comes in this beautiful, brilliant blue color. It's very, very shiny. I took a little bit of souvenir from the lab after
So that
I
is
graduated.
not like a GNC order. That is not like ordered from anywhere. That is a very
No.
Okay.
It's very, very dilute, so it's very, very safe. I was allowed to take it as a little souvenir for myself.
What are there any safety concerns with this particular element?
Itself is safe. What's their names? Bodybuilders take it as a thing to bodybuild.
Okay, so it might be a GNC.
Oh, okay. I'm not sure. I have no idea.
In the US, that's like a dietary supplement drug company.
Oh, okay. I don't know if it exists on its own. Maybe it's added. I'm not sure. Again, it's the other thing that's used in steel. So do you know iron is usually mixed with something? Vanadium is the thing sometimes that's used in the mixture as well.
Nice.
So it's not a dangerous element in that case. The thing that makes it dangerous, or why people flag it, is because of the acid that's in it. So it's H2SO4, sulfuric acid. Same thing that's in your car battery. If you have a lead acid car battery in your car, it's the exact same concentration as well, 4.5 molar. So it's not much more dangerous than that.
Right. So don't drink it.
No, yeah, don't drink it, of course. Now, so what's really, really cool about vanadium, and this is the selling point, is that vanadium exists in 4 oxidation states. And I actually prepared for this talk ahead of time. If you will bear with me, I have a really cool thing to show you, if everyone is okay with this.
Please.
I have a really cool whiteboard with all of these stuff. Now, make sure that you guys get to see it. Hopefully you guys can see some of it above my head.
Looks perfect.
Is it visible?
Yep.
Nice. Okay. So this is a very simple structure of a vanadium flow battery. And we have a membrane in the middle, which is usually most batteries have half cells, which means it's split in half with something on one side and something on the other for every negative, positive reaction. On the positive side, we have 2 oxidation states, vanadium 4 and vanadium 5. I showed you vanadium 4, it's blue. Vanadium 5, its different oxidation state, exists in a brilliant red color. Vanadium 2 and vanadium 3 are on the negative side of the cell. Vanadium 2 is purple, it's really, really bright purple, and vanadium 3 is green. It's actually insane how colorful vanadium is in these oxidation states. It's incredible, which is very important for spectroscopic analysis, which is a very, very important field of research in it. And so when the battery is discharged, it's in vanadium 4 and vanadium 3 oxidation state. We charge up the battery, vanadium 5, vanadium 2, becomes discharge, vanadium 4, vanadium 3. And that is the charge-discharge cycle. And where the word vanadium flow battery comes in is that you actually have 2 giant pumps then on either side that are continuously pumping this electrolyte. So let's say you needed to store, all you have to do is add more electrolyte to your station or to your area of energy storage. So you could customize it to what exactly you need for your electric grid.
And how is that going to differ per different electric grid? Like how do you infer what the customization needs to be?
Oh, it depends on every little island and every country. So I know Japan does a lot of these, Japan has loads of vanadium flow battery actually. Because they have little islands. So they have their mini grids on their little islands, and then they have big interconnection with the main lands, I think, if I'm not mistaken. But then you have something like China. China's built the largest vanadium flow battery infrastructure 2 years ago, I think. It was quite new. It was absolutely massive. And they just needed to literally store excess energy. And so what you're using these giant vanadium flow batteries, ideally what you would use them for, is that, remember I said that you have all the inertia, all the different response times to buy you time. A vanadium flow battery can respond very, very quickly. It's one of the quicker forms of batteries to be able to respond to this and to provide a stable power. But it can only provide power in the most ideal situation. I think that the most giant, amazing vanadium flow battery plant that you could have could buy you 20 minutes.
Okay.
The idea is this isn't like oxygen not included or one of those games where it's a way of storing massive amounts of energy. All it really is doing is buying you time so they can efficiently respond to the grid, as in add a new power source, let's say a wind farm or another solar array or anything like that. The battery systems in most countries, in any countries or islands around the world, aren't there to store huge amounts of energy. All they're really designed to do is buy you that valuable time that I spent so much time talking about initially.
So that is to kick back on. And does the vanadium battery allow you to have that buffer to be able to know what exactly is it working on, like in a way that it can help? I guess that's the question.
What I mean when I say that it uses free energy is that it's energy that's being wasted anyway. So sometimes wind is blowing a little bit extra windy that day. Sometimes we get a little bit of extra sun. That never happens in Ireland, by the way. But on one occasion or two in the last 2 years, we might have had a bit of extra sun. And so when you have this excess, that's when you can use it to store the energy. So you're never actually wasting. Remember I said that was a big problem with the wind turbines, that you're purposely operating them at 80%. Mm-hmm. You're purposely operating all of these renewable forms of energy at lower percentages to be ready to compensate for the stability of the grid. And so if you do this way, you're not being wasteful.
That's a really cool way of taking it. A question from chat is, what is the purpose of the different isotopes?
Oh, the different oxidation states of vanadium.
Yes.
It's the reaction electrochemically that happens. The purpose of it is the way it's an electrochemical form of energy storage. So on the positive side, if vanadium 4 goes to vanadium 5, it's a higher energy state. It stores electrochemical energy as vanadium 5. So when you bring it down to vanadium 4, you're getting energy back out of it. We'd have to do a whole electrochemistry lesson if we wanted proper answers there.
Is there any byproduct to using a vanadium battery? Like, what is the end result, right? Some batteries aren't recyclable. You have to dispose them in particular ways. Like there might be leaching into the soil, right? There's like some negative consequence of it. But with the vanadium batteries, is there anything?
Yeah, no, that's one of the biggest selling points of vanadium. Like we cannot compete, we can't compete, but I'm not competing against lithium ion batteries. I'm not coming after anyone. But my point is vanadium flow batteries cannot compete with lithium ion because they're hugely energy dense. They're so energy dense, they have the energy density of a live grenade. They're very, very energy dense. And there are those whole discussions and spiels about the dangers of it. Because vanadium flow battery number 1 isn't that energy dense, it is so much safer. It's also very, very much based on the practice of lead acid batteries. And lead acid batteries have been around for a very, very long time. It's one of the older form of batteries that we know. If I'm not mistaken, correct me if I'm wrong, it is the first recyclable battery that ever existed. And so we know the recycling process of lead acid batteries. And very similar, we know vanadium. Now, how we get vanadium is via mining. And you don't actually mine for vanadium. You just accidentally find vanadium when you're actually mining for useful stuff, if that makes sense. So it's just a byproduct of mining. So obviously there are the usual worries and problems with any sort of mining that does happen, but it's not something that you're going out of your way for already.
So what else is vanadium used for anything else?
Just like I said, the bodybuilders take it as supplements and it's used in steel. It's the addition to steel. I'm trying to think of anything else.
Is it common enough where it's, because you were saying you don't have to go looking for it? So is it just, you just happen to be digging for something else? Like, oh, we got some, we can sell it on, and that's good. Like there's enough of it around.
I want to say there is enough around it because not many people are using it yet. Now, if I say this and I don't know, become the president of some country and I suddenly promote vanadium flow batteries and everyone wants it, there won't be enough. Absolutely.
Gotcha.
At the moment, the countries that do have mining access to vanadium are probably a lot more advantageous. I know that's why China was able to build the biggest one they had access to. I know that we got vanadium from Japan. So Japan has access to it. And I think Canada and Russia are the other two countries also who do have access. So it would definitely benefit those nations if they were looking for new forms of energy storage and things like that. I'm a really big advocate for not narrowing down to one single form of energy. Number one, storage or energy production. In terms of stability, financial stability, and also to a certain degree, grid stability, I am a big advocate for diversifying energy storages and energy sources.
So that's a follow-up question from chat is when there's, wind, solar, hydro, all these other types of powers, is there something that's better overall? Or is it just, again, grid dependent, system dependent, and maybe a mix of everything would be the best thing to do?
Oh, I said that all renewable is a DC, which is bad in terms of stability for the grid. But there is something that is good and is good for stability. Dams, hydro power plants. They're very, because it's, even though it's not steam, technically,
the water's still flowing and turning.
Exactly, turning a turbine, exactly. Obviously, you have problems like floodings and droughts and all of that. But generally speaking, that is a really cool form. Honestly, capitalizing on your nation, your geographical ability to harness natural powers is probably the best description or advice I can give. In Ireland, we have wind. Hell, we've a lot of it. So I'm a big advocate for capitalizing on that. And then, Iceland has the amazing access to geothermal, which is great as well. So I'm a big advocate for that for sure. Depending
on the locale you're in, that's what you would adapt to, how to best able to fix things and be able to figure out what to actually do, right?
Exactly.
Nice. Makes total sense. So, okay, so you're working on this battery.
Yeah.
Right? Vanadium battery to be able to pick up the temporal difference to make 20 minutes. What does that PhD look like?
Oh yeah, my PhD then is a bit more boring. So ultimately, two of the chapters were focused on the thermodynamic potential of all the vanadium oxidation species. That doesn't sound very, very fun, but no one had done it, so it was actually really, really cool. I was able to build two different experiments and compare and contrast them and basically simulate a more ideal battery. Wasn't able to test it just because of time. I was already doing my PhD for 4.5 years. My funding ran out. I had to write a thesis. But there's definitely a lot of continuation work behind it. Then the grid stuff was mostly simulation, integrating a battery with the Irish electric grid. I got data from EirGrid, which is our operating electric grid entity. I'm not sure what their name is exactly. But yeah, I contacted them. I was like, look, I'm doing a PhD thesis. Could you give me frequency data? Which I didn't realize how much data it was, but every second of the grid was monitored, every single second. So there was a data for every single second of Ireland in 2019 and 2020. And I had to analyze that frequency data to simulate the whole spiel that I was working on.
So what does the simulation entail, and how difficult it is to go from something that you can test to that simulation? Like, because we, a lot in like bioinformatics, it's like, well, it's almost like garbage data in, garbage data out in terms of what you have to simulate with. How do you know what is good data when you're doing the simulation? How do you know the simulation has been a worthwhile output?
Okay, I see. Okay, so the conditions of my simulation were, I'm going to introduce a new concept. We've talked about the electric grid and stability. There was a lot of things I said. So going back to it, a thing happens on your electric grid. We call them events. So what is an event? An event is where, remember I said the electric grid in Ireland operates at 50 hertz, in the United States it's 60 hertz. If your grid starts to rise a little bit too high, or if it starts to drop a little bit too low, that is defined as an event. It means that there is a moment of destabilization in the grid, and you have to respond to it accordingly. If it arises above 50 hertz, it means you need to integrate an energy storage. You have too much power on the grid. So this is where the excess energy storage comes in for battery storage that I described. And that's what I would simulate. Would the battery be able to sustain itself by consuming this excess power of these events? And vice versa, an event where it begins to drop under 40 hertz, you need to feed power back into the grid and would the battery be able to sustain and respond to those events? And there was different definitions for events, what kind of percentage or what kind of parameter. You can imagine that the electric grid is very, very sensitive. And so let's say you defined, turn the battery on when we reach 50.01 hertz, but it'll be playing with that 50.01 hertz like a fiddle, like it'll be up and down, and you can't have a battery shutting up and shutting on and off all the time. So there's all these different scenarios and conditions that I had to simulate, and that was mostly what I did with that work, to publish and to show all the kind of conditions to make a battery, a vanadium flow battery, work. And ultimately, what's really cool about the work that I did is that it doesn't even matter if it's a vanadium flow battery. It's just a battery, a form of energy storage that could be integrated with the grid.
Dr. Tofu, how does something like this look physically? These vanadium batteries in a plant, like what am I envisioning here?
2 huge giant tanks, one with the negative side of the electrolyte, one with the positive side of the electrolyte, and basically 2 giant plates where the carbon electrodes can be immersed into the electrolyte to do all the bzzz stuff.
So the drawing that you had behind us, but with 2 giant tanks.
Exactly. So I don't know if you've seen lithium-ion battery energy storage facilities. They're like literally rectangular plates stacked and in these big giant containers, which are also stacked. In this case, it's just one infrastructure, one building with a giant tank.
Cool. And what are the safety features for something like this? Is it as much as it is for, like, let's say, nuclear power, or is it as little as it might be for, like a water supply?
Yeah, not as little as with water supply, there's a lot of danger mechanically. Like, you're working with a lot of heavy duty material, which is, there is its own safety. But in terms of, it's nowhere near as nuclear. It's way safer than lithium. I would describe it as the battery being very similar. Imagine that it's just a giant car battery. Mm-hmm. It's not that different than the giant car batteries that you have inside your car. Again, it depends what car you have. I'm talking about classical, if you turned on the lights, your parents would scream at you kind of car. that kind of car.
Nice. And the question was too, like, how big is this tank that we're talking about? Like, is this something like a football field size, a car size?
That's the most. I always make a joke about this when I see imperial units being used, and instead of converting them to SI, it's like, it's 2/3 of a football field or 10 chihuahuas. Instead of why? No, I've never seen a real live giant infrastructure, because we don't actually have a vanadium flow battery infrastructure here in Ireland. In case I kind of gave the impression, we have built the first electrical energy storage here in Ireland, in the centre of Ireland. It is lithium ion in collaboration with a Korean team. But again, I've never been at a large actual vanadium flow battery infrastructure. I think if you are interested in looking it up, if anyone in chat is very interested, Dalian, China, that's the one that has built the biggest vanadium flow battery in the last 2 years. Absolutely incredible work, and they've doubled it in size recently, which is really incredible. So if you're looking to see it, and just to kind of jump on the question of saying, is it still experimental? It is, what's that word where it is integrated in real life with grids, or like it's definitely already installed with electric grids around the world, in Germany, in China, in Japan, but they're not mass commercial.
Gotcha. So I don't know if there's
like a word.
It's in like a flavor of testing phase. Is that fair?
Yes. So it's definitely already past test. Like, I think you can even buy vanadium flow batteries commercially. There are websites in the United States anyway. They're kind of advertised, I think, in New York, if I'm not mistaken, in the basements. They're considered very, very safe because they can't explode.
Fair. I was just going to be like, wait, what do you use them for? Okay, that's also a need that it's like in that different zonal thing. So it goes to show, right, the importance of doing the theoretical work. Like, you don't need to have that real life machine next door to you. The importance of the theoretical side of things to inform what the real life might be doing. We had one question in the chat of, can you tie the technical and the engineering side of things? Like, could you describe to folks why that's also like one of these like more hard sciences? Like, it's like in the same vein as the biological and the chemistry side of things. Of like, I feel like some of it, as people are saying, it's a little bit abstract, and so it's like, how do we make it so that it, how can we explain to folks that it is a real life, like really heavy hitting science, if that makes sense? As in, like, it's as easy to make like direct impact as something in the like working with cell lines. Like here, I'm working with cells in a dish that has an immediate impact on people. You're working with these batteries that has an immediate impact as well.
Yeah. So I suppose I still have the unfortunate disconnect that I'm not working with a company and I am not working with an actual commercialized electric grid to do it. The research that I do in the lab is very fundamental. Like I said, in the end, what I did was I measured doing two very interesting experiments. I measured the thermodynamic potentials of all these 4 vanadium species, and no one in the commercial realm or engineering realm would do that. That's a very I don't in chemistry. Do you know the way you measure the chemical thermodynamic potential of all the species of anything, H2SO4, HCl, any existing chemical out in the world you would measure? For some reason, the different oxidation states of vanadium weren't done, and that's why I went off and did what I did, which was, I suppose, as raw science as it gets. It might not be fun in terms, it doesn't look that glamorous, it wasn't revolutionary, but it is a very defined parameter.
So similar to in the biological side of things, where you're trying to identify how exactly things work on a fundamental level, and then it'll be informative later on. But this is work that needs to, like, the very basic work for a whole understanding of how the system works.
Exactly. I did want to talk about this, but I really mostly wanted to talk about how amazing my experience has been, and how I have been so lucky in my life that I am coming off from the shoulders of giants before me. And what I mean by that is, as I did my master's and my PhD, there was no obstacles in my way to stop me from getting my master's and my PhD and becoming the physics lecturer that I am now. I did not experience sexism or nasty commentary or any, degrading aspects that are usually associated in this area. I also was able to have women to look up to in my own field. I had women in physics that I was looking up to. I had women who were doing PhDs alongside me through my path. And so what I wanted to highlight, it's not to negate the difficulties that women are going through, because that's very important to point out, but rather to show that progress is being made, that I am standing on the shoulders of giants. I am standing on this ground where so many women have paved the way ahead for me. And I got to have this really privileged and amazing experience being a woman in STEM. Just a little kind of like side rant on the topic, which I wanted to be like a guest in the middle to kind of cheer up people a little bit that there is some progress being made. But you know what? If it's to start it off as well this way,
I think that's an inspiring way to kick off the whole series of, like, there is and has been progress. Yes, there's work to do, but it's really refreshing to hear that someone did have a good experience. And I think that could be very inspiring for the next generation of women in science who are listening to this show, whether either live or later on, and seeing like this extremely successful PhD in physics, Twitch partner, hopefully soon to be Twitch ambassador, is telling us about the science that she works on and being able to feel supported in the field. And it's not all just a battle.
Oh, yeah. No, it is really amazing. And I wanted to highlight again, just to say that obviously improvements can be made. And what I experienced was definitely a privileged experience, and it's not majority, unfortunately. But I'm very, very lucky. Absolutely.
Do you have any broad advice for women trying to get into the field of STEM? What, like, any guiding words that you feel might help or would have helped you had you known?
Doing what you love is, I know it's cheesy. I know it's overused. Everyone says it. Everyone does it. But my life has been really, really fortunate, really lucky, really amazing. I have been describing it lately that I am having such an amazing life with Twitch, with my job, with everything that I do in STEM, because I love what I do. I love to learn. It's definitely something very primitive in me, that no matter how fundamental the physics is, even if it's first year physics, stuff that me and you guys could learn right now in the next 15, 20 minutes, I love to always either revise, to learn, or to apply a new twist to what I'm learning. And if you have that passion, it doesn't even matter if it's STEM, to be fair, it could be anything. I absolutely advise you to pursue it. And I know it's very sad to say that, because sometimes dreams aren't applicable directly to job and employability. But whatever it is you do, maybe you can get the closest thing to it, or something that you can do as a hobby that you absolutely love and appreciate. That's my advice there.
That's absolutely beautiful. Dr. Tofu, thank you so very much for joining us, for supporting the education on Twitch, women in STEM, and just everything that you do. Thank you so very much.
Thank you so much. Yeah, perfect. Bye.
Thank you, Dr. Tofu.
Bye, everyone.